So today we'll look for one of the code base which I have written for the bare metal. So in this code actually we can run bare metal kernel in RPI 3B. Okay, so RPI 3B, you may be knowing, he has ARM total 4 cores of ARM A53. Okay, so RPI 3B has total 4 cores of A53, ARM A53. Okay, so today in this video I will discuss about the folder structure. Okay, how these codes are structured, and then one by one we will go through the code, and I will try to explain the each block of code so that we can understand how the execution starts, how the boot happens, then after boot which firmware is loaded, then how it jumps to the kernel, and inside the kernel how it initializes different UARTs, peripherals and all. So that and all we will discuss. Okay, so the contents which we are going to cover in this videos are like high level, we'll go through the high level overview. Okay, so folder overview will go, then next we'll go through the what are the prerequisite to build this binary, to build this kernel image. What are the prerequisite? Mostly that prerequisite is you need an cross compiler, GCC cross compiler, and maybe some extra build tools is also required. So that also I will discuss in a separate video, because for that I will try to show in the Linux system. This is Mac system, so that's why I will not show this, but just I will say what all things are required for this. Okay, so here mostly we need a cross compiler and some build tools. Some build tools had some dependency, this cross compilers had some dependency on that build tool, so that we need. Okay, and then I will explain about the boot flow, how the core boots up from the from startup script till your main function. Okay, so that boot flow I will explain. Then after that boot flow we will talk about the linker script memory, basically linker script. So this linker script is actually used to place the kernel in the RAM. Okay, so this RPI 3B has a RAM, and this kernel whatever you will compile, where to place this inside RAM, and this is actually defined by the linker script. So basically whenever you compile the code, it has many sections like text, data, BSS, then you will have stack, heap and all. So but basically the startup there is a underscore start function that should be placed at the correct location. Then only the GPU firmware, actually GPU firmware means in this RPI 3B we have a GPU as well as CPU. So the responsibility of booting from the reset is on GPU. Okay, after GPU first initializes its sum of its contents, and then it give controls, it give control to CPU. Okay, so that's why we need to place this kernel at a particular location, then only where the GPU gives control, where GPU gives control to the CPU. Okay, control to CPU. Okay, and after that we will discuss, I will show you the code, how the exception vectors are defined and how the code jumps to the exception vectors. Okay, and after that there will be some tips on how to go through the code and all. Okay, tips for troubleshooting, so tips for debugging basically. And here I will mostly give debugging tips based on UART prints. Okay, because we can have multiple ways to debug, but you can have debugger and all, but that those machines or those systems are very costly. But you can order yeah, but we can use UART. UART is the best and the cheapest way to debug. UART for UART basically you need to order a TTL logic converter, USB to TTL logic converter. Okay, that you can get in Amazon and all, USB to TTL logic converter. Okay, at least this you need for debugging, and this will not cost much. It will come around 100 to 200 INR. Okay, so let's start one by one. We'll go through the code. First the folder structure. Okay, so inside this arm-stub, let's go through the, before going through arm-stub I want to show you the hierarchy. So we have one folder as arm-stub, where we have one assembly armstub.s, and then we have some include folder where we have all headers for all the files which are there in the source. Okay, so this is how it is organized. So all C and assembly is organized in the source, and all header files are organized inside the include folder. Okay, so the first thing which I want to tell is basically your this by default, if we don't use there's a arm-stub. Okay, arm-stub is the code which is basically loaded by the GPU firmware, and there is a specific reason for this arm-stub. If we don't use this arm-stub, right, so what happens, this is basically used to bypass the exception level jump from EL3 to EL2. Okay, so what happens, right, whenever the CPU boots, it boots up in at EL3 exception level. Okay, so let me first tell you the exception levels. So total 3 exception levels are there, total 4 exception levels are there, that is EL3, EL2, EL1 and EL0. Okay, so basically whenever the CPU boots, it boots at EL3 after the reset, and then we need to do some initialization at EL3. It jumps, after that it jumps to EL2, then EL1 and EL0. So mostly at EL3 all your boot related initialization will happen. Okay, so like setting up IRQs, IRQ vectors. So we need to set up the IRQ vectors at each exception level. Okay, at EL3, EL2, EL1, and we also need to set up this. So we also need to set up the what we call we also need to set up MMUs and all, okay, at different exception levels. Okay, so basically this mode is called as this one I don't remember, but this one is called as hypervisor mode. Okay, and EL1 is where the kernel executes. This one we call as a kernel mode, and basically all the applications executes at EL0. Okay, so what I'm trying to say that at EL3 the CPU boots up, and there is a arm stub which is by default inside the GPU firmware, which brings the CPU from EL3 to EL2, and then it gives control to the uh, kernel, to the CPU kernel. Okay, to the kernel. Okay, so what we try to do, we try to replace the arm stub with this arm stub. Okay, for that what we try to do, we try to write one magic stub magic. This number actually is searched by the GPU firmware to load this arm stub. Okay, so whenever it loads this compiled arm stub, it, instead of changing the exception level from EL3 to EL2, basically it will directly give control to the uh, start of the boot code, that is at the 0th location. Okay, that's why we write this arm stub. If we don't compile and load this arm stub, what will happen, the exception level at the at this boot as code, right, at this startup will be at EL2. If you want this start code to be executed at EL3, we need to load armstub. That is the only purpose for this armstub. Okay, and once that armstub is loaded, and then the start will come, the execution will start from here. Okay, so here what it will try to do, it will try to execute, try to find the primary core. Okay, and all this here you can, there is a way to find the exception level, that also you can save in one of the register. Okay, but that I will show you directly if I jump to the kernel.c file. There we have written a code to find the exception level. There is a register from where we can read what is the current exception level. Okay, so once it jumps to start, so here uh, as I explained earlier, right, total 4 cores are there inside the ARM-A53. Okay, so what we try to do generally, right, we try to let other 3 cores, that is total, suppose if I indexed core 0 1 2 3, so the core 1 2 3, what I will put there those cores in a spin mode, and I will allow only core 0 to first set up some of the MMU and do that jump the exception level and jump to EL1 and then jump to main. Okay, what other cores will be doing, other cores will be directly, basically if you read this register MPIDR EL1, so this register will be read inside X0, and we are trying to see only lower 8 bits. Okay, then comparing with X0, and if it is 0, then it will go to proc hang, otherwise it will jump here. Okay, so core 0 will jump to the master, and rest of the cores will jump to the proc hang, and there it will be in the wait for event loop. So it will keep on looping here other cores. Okay, so first the code here I'm trying to do is, first I'm trying to first the core 0 CPU will come up, and after that other cores will come up. Okay, we will do one to remove the other cores out of the WFE, we have to execute one instruction. Whenever we execute that instruction, then this course will come out of this and start executing from the master. Okay, so first we set up the core 0, and here what things we are doing, we are trying to disable the MMU on the core 0. Okay, then we are trying to set the hypervisor EL2 register, EL3 registers, and SPSR. So SPSR is your stack pointer register. So SPSR value is also defined here inside this file common.h. Okay, sorry, not common.h, it is defined inside sorry, I have, so this macro, right, SPSR value, this is defined here inside sysres.h. Okay, so basically this what it will do, it will do masking of that EL1 EL2. Okay, I'm thinking that before giving this video I should have discussed different exception levels and how that stack pointer, what all things are needed to set up a CPU. So those things I think I should discuss first, and then I should go on this one. Okay, let's continue. uh, Parallelly I will make a separate video on each of these concepts. Okay, so basically if it executes this code, after the execution of this code, core the exception level for the core 0 will jump from EL3 to EL1. Okay, and in that, after this then EL1 we will what we'll do, we will initialize the BSS section to all zeros. Okay, here, and then we are setting the stack pointer, so we have to give the location of stack pointer, and after that we'll jump to the main function. Okay, so I think this bootest.code is clear ki what we are trying to do here. Basically if I summarize it, so from the armstub.s it will jump to this start at EL3 exception level. It will find out which, it will put other cores in the WFE mode, and only core 0 will start executing. Core 0 will execute this master code where it will disable MMU, and it will prepare all the registers to jump from EL3 to EL1. Okay, and finally the EL1 entry will be saved inside ELR3 registers and just give ERET. So basically we are jumping from the EL3 to directly EL1. Okay, so at EL1 we will basically initialize the BSS section, then setting the BSS section to 0, and then so this mem0 is also one tag which is defined in the entry.s. Okay, so I will do a video for each of them. Sorry, somewhere it is defined, where I have defined this mem0 dot, okay, it is defined dot in mm.s. Okay, where I am just trying to make all those values as 0. Okay, so this is that jumping to mem0, and after that we are setting the stack pointer, then jumping to kernel main. Okay, so basically the core 0 will jump to the kernel main. Okay, so inside kernel main I'm trying to give overview in this video only. The each detailed video I will do for each of the files separately. Okay, I think mostly I have explained the startup boot.s file and armstub.s, what is the use of that. Directly it will, then after that boot.s it will jump to the kernel.main. So here the first thing which we set up is the UART, because that's what we are going to use for debugging. Okay, that's why we are doing UART in it. There is a function to print directly some string on the UART console. Then we are initializing IRQ vectors, interrupt controller, IRQ enable and timers. And basically if we jump here, then at least our we have jumped to EL1 kernel level, and then we are doing all this initialization. Okay, so there are each of this code I will explain one by one, but I think this video I already recorded for lot of time. Okay, I will stop here. Then next video I will do, I think, one by one for each of the files. Okay, yeah, thank you.